Wow. Reading the datasheet and this hobby is really boring sometimes. And I'm just searching for the the enthusiasm to keep going. So anyway, continuing on with timers. So I think I left off here, page 24. So continuing on. So I'm not going to try to cover that again, but the prescale was different. Register associated with timers, timer 0, TMR0, option, trace GPIO 1. Just a reminder to cover that. Timer 0, 8-bit real-time clock / counter. Legend, shaded cells not used by timer 0, unimplemented. Using timer 0 with an external clock. When an external clock input is used for timer 0, it must meet certain requirements. The external clock requirement is due to internal phase clock TOSC synchronization. Also, there is a delay in the actual incrementing of timer 0 after synchronization. External synchronization. When no prescaler is used, the external clock input is the same as the prescaler output. The synchronization of T0CKI with the internal phase clocks is accomplished by sampling the prescaler output on the Q2 and Q4 cycles of the internal phase clocks. Figure 6.4. Therefore, it is necessary for TOCKI to be high for at least 2 TOSC and a small RC delay of 2 TT0H, and for at least 2 TOSC and a small RC delay of 2 TTOH. Refer to the electrical specification of the desired device. When a prescaler is used, the external clock input is divided by the asynchronous ripple counter type prescaler, so that the prescaler output is symmetrical. For the external clock to meet the sampling requirement, the ripple counter must be taken into account. Therefore, it is necessary for the TOCKI to have a period of at least 4 TOSC and a small RC delay of 4 TTOH, divided by the prescaler value. The only requirement on the TOCKI high and low time is that they do not violate the minimum pulse width requirement of TT0H. Refer to parameters 40, 41, and 42 in the electrical specification of the desired device. So I asked ChatGPT for a very simple explanation of timer 0 before I continue on. Sure, timer 0 in the PIC10F200 is like a tiny stopwatch inside the microcontroller. Here's a simple breakdown. 1. Counts time. Timer 0 counts up from 0 to 255, kind of like counting seconds on a clock, but much faster. 2. Speed control. You can make it count faster or slower by adjusting a setting called the prescaler. It's like changing the speed of the clock's ticking. When timer 0 reaches its maximum count, 255, it can alert the microcontroller to do something like ringing an alarm when time's up. This alert is called an interrupt. 4. Uses. Timer0 can help in tasks where you need to measure time or create delays, like blinking an LED at regular intervals or keeping track of how long a button is pressed. So, Timer0 is a handy tool in the PIC10F200 that helps with timing and creating precise delays. Let's see if ChatGPT can summarize this stuff. Come on. So I used the image to text, and I'm going to just barf this into ChatGPT. Have fun explaining this one. I don't even care to think about it that much, so maybe it can do the work. Using Timer0 with an external clock. When you use an external clock with Timer0, it has to follow some rules. This is because the microcontroller needs to sync this clock with its own internal clock. Also, there is a slight delay when Timer0 actually updates after syncing. External clock synchronization. If you don't use a prescaler, a setting that slows down the clock, the external clock input directly affects Timer0. The microcontroller samples this clock at 2 points in its cycle to sync it correctly. The external clock signal must be high for a specific amount of time, at least 2 cycles of the internal clock plus a tiny delay, and low for the same amount of time. With prescaler. When you use a prescaler, it slows down the external clock before it reaches Timer0. The slowed down clock must still be high and low for a specific amount of time, but the exact time depends on the prescaler value. The high and low times must also be long enough to meet the microcontroller's minimum requirements. Refer to the microcontroller's electrical specifications for the exact timing. This keeps the essential information, but it makes it easier to understand. Actually, I find that it really didn't explain anything, and I'll just tell it that. Anyway, I did read it, so. Okay, Timer0 increment delay. Since the prescaler output is synchronized with the internal clocks, there is a small delay from the time the external clock edge occurs to the time the Timer0 module is actually incremented. See figure 6.4, and it shows the delay from the external clock edge to the timer incrementing. Timer0 timing with external clock. External clock input or prescaler output with a little 2 next to it. External clock prescaler output after sampling. Increment timer 0, Q4, timer 0. Delay from clock input changes to timer 0 increment is 3 TOSC to 7 TOSC. Duration of Q equals TOSC. Therefore, the error in measuring the interval between 2 edges on timer 0 input equals plus or minus 4 TOS max. 2 external clock if no prescaler selected, prescaler output otherwise. The arrows indicate the points in time where sampling occurs. I guess between Q4 and Q1, and between Q2 and Q3. Okay, this goes back up to the previous page. Just trying to roll through all the instances of timer 0, and maybe a timestamp here. Okay, so yeah, maybe a timestamp here because now I'm going to be talking about the prescaler. 6.2 prescaler. An 8-bit counter is available as a prescaler for the Timer0 module or as a postscaler for the Watchdog Timer WDT, respectively. See section 9.6 Watchdog Timer WDT. For simplicity, this counter is being referred to as prescaler throughout this data sheet. Note, the prescaler may be used by either the Timer0 module or the WDT, but not both. Thus, a prescaler assignment for the Timer0 module means that there is no prescaler for the WDT and vice versa. The PSA and PS 2 to 0 bits, option 3 to 0, determine prescaler assignment and prescale ratio. When assigned to the Timer0 module, all instructions writing to the Timer0 register, example clear F1, move WF1, BSF1, X, etc., will clear the prescaler. When assigned to WDT, a clear WDT instruction will clear the prescaler along with the WDT. The prescaler is neither readable nor writable. On a reset, the prescaler contains all zeros. Switching prescaler assignment. The prescaler assignment is fully under software control, i.e., it can be changed on the fly during program execution. To avoid an unintended device reset, the following instruction sequence, example 6.1, must be executed when changing the prescaler assignment from Timer0 to the WDT. Example 6.1, changing prescaler, Timer0 to WDT. 1, 2. Changing prescaler Timer0 to WDT. Although I don't think I'll be using the Watchdog timer, but hey, some sample code. Never a bad idea to study. Clear WDT. Clear the Watchdog timer. Clear F, Timer0. Clear Timer0 and prescaler. Okay, I was looking for the Timer0 register, and I'm just not finding it. But I think that's because it's just like 8 bits or something. Yeah, like this is on page 24, registers associated with timer, and it shows Timer0 in bits 7 to 0 are just real-time 8-bit real-time clock / counter. Okay, so I was reading this code. Clear F, Timer0, clear Timer0, and prescaler. Move LW 00XX 1111, and then put that in option. I won't examine that. That would be neat though. Okay, I am looking at it. So here's the option register. So the GPWU and the GPPU both are disabled with a 1. So they're both enabled. So they enabled the wake up and they enabled the weak pull-ups. And then I guess it didn't matter the timer source. They just put an X and the TOSE is an X. And then they set a 1 increment on high to low transition. Prescaler assigned to the WDT, and then they set the prescaler to 1 to 256. That's what they did here in this code. Are required only if desired. Clear watchdog timer, PS 2 to 0 or 0 or 001. Move LW 001. Set post scalar. Option desired WDT rate. Well, I don't fully understand that. Let's just throw that code at ChatGPT. Explain this about the PIC10F200. Yeah, so I did actually ask it that, and it surprisingly handled the question. I'll just read this quickly. This command resets the watchdog timer to prevent it from timing out and resetting the microcontroller. This command resets timer 0. MoveLW loads the W register with a value. In this case, the value is 00XX1111, where XX are placeholders for other bits. Move WF moves the W register to the option register, setting the desired prescaler value. This command ensures the WDT is reset again after making changes. MoveLW loads the W register with a new value. In this case, thus, sets the post scalar to the desired WDT rate. Explanation of key points. Clear WDT resets the watchdog timer. ClearF TMR0 clears timer 0. Move LW. Okay. The exact values for XX and that depend on the desired prescaler and postscaler settings for your specific application. Okay, moving on to this next page. To change the prescaler from the WDT to the timer module, use the sequence shown in example 6.2. This sequence must be used even if the WDT is disabled. A clear WDT instruction should be executed before switching the prescaler. Example 6.2. Changing prescaler WDT to timer 0. Clear WDT, and prescaler. Move LW, select timer 0, new prescale value, and clock source option. Okay, so I asked ChatGPT the question whether you can switch the prescaler back and forth to timer 0 and WDT while the microcontroller is operating or running or iterating. Can you do that? I'm not even exactly sure the question I'm asking, but it seems to have come up. Yes, you can change the assignment of the prescaler between timer 0 and the watchdog timer while the microcontroller is running. However, this must be done carefully to avoid disrupting the operation of your program. Here's how it works. Okay, I guess I'll read this. Prescaler basics. Prescaler assignment. The prescaler can be assigned either to timer 0 or to the WDT, but not both at the same time. This is controlled by bits in the option register. Switching prescaler assignment. You can change the assignment of the prescaler during runtime by modifying the option register. This means you can switch the prescaler from the timer 0 to the WDT and vice versa while your code your code is executing. Practical considerations. Timing impact. Changing the prescaler assignment will affect the timing of both Timer0 and the WDT. Ensure that the timing requirements of your application are met after the change. Interrupts. Be mindful of any interrupts that may rely on Timer0 or the WDT. Changing the prescaler assignment might affect the timing of these interrupts. And here's some code. This sets up the option reg, clear watchdog timer, switch prescaler to WDT, so it clears the watchdog timer, moves a value into the option register. It's interesting it's doing it this way. Didn't know you could call it that. Who knows if ChatGPT is even getting this right? That's another question. Switch prescaler back to the timer. Clear watchdog timer. Clear WDT to prevent immediate timeout. Move LW. Set prescaler for Timer0 with a division factor. Load value into option register. I'll read it. Explanation. Number 1. Initial setup. The prescaler is assigned to Timer0 with a specific division factor. 2. Switch to WDT. The prescaler is reassigned to the WDT by updating the option register. Switch back to Timer0. The prescaler is reassigned to Timer0 by updating the option register again. Important notes. Clear WDT. Always clear the WDT before changing its prescaler to prevent an unintended reset. Timing. Verify the timing requirements of your application are met after changing the prescaler assignment. By following these steps, you can dynamically switch the prescaler between Timer0 and the WDT during the operation of your microcontroller. It's funny how I find ChatGPT more convincing than the datasheet, even though the datasheet's probably more authoritative. Okay, to change the prescaler from the WDT to the Timer0 module, use the sequence shown in 6.2. This sequence must be used even if the WDT is disabled. A clear WDT instruction should be executed before switching the prescaler. Changing prescaler WDT to Timer0. Clear WDT, move this value into the option register, which I suppose, what does bit 4 do? Well, no, I guess it was bit 3. Prescaler assignment bit. Assigned to the WDT or to Timer0. 0, 1, 2, 3. So it's the PSA bit. Block diagram of the Timer0/WDT prescaler. TCY equals frequency oscillation divided by 4. And that goes into the multiplexer and sync 2 cycles. Here's the GP2 pin, TOCKI pin, and the TOSE pin. The TOSE pin was selecting on the high to low transition or low to high transition, and I covered that in a previous diagram example in a previous video as to how that actually works logically, and it's interesting because it actually does. Timer0 reg, data bus. PSA, that's the prescaler assignment. I guess this is multiplexing. TOCS, what was that again? Timer0 clock source select bit. That's selecting GP2, TOCKI, or the internal clock. So that's what that's doing. And this is the prescaler assignment, which can choose what, the watchdog timer, or I guess it can choose the watchdog timer, or it can select timer Then it comes down into this multiplexer, and it's got the prescaler assignment here again, somehow connected to a multiplexer. So here's the block diagram. Is that the same multiplexer it's talking about? Where's the timer 0? Here's timer 0. And here's the watchdog timer over here, which kind of has a roundabout way of going to the multiplexer. But I guess the watchdog timer roundabout way, and the timer 0 can go to the multiplexer. This is the WDT enable bit. Funny, I won't be covering the watchdog timer. Well, I never say never, but I don't intend to cover the WDT in this series of videos because the code I'm planning on using isn't going to use the watchdog timer, but I'm just doing this to understand more about the chip. 8-bit prescaler, 8 bits to mux. It's got the prescaler WDT out. Well, having said that, maybe I should ask ChatGPT to briefly explain what the watchdog timer does. Then I don't have to read the data sheet on that. Alright, that's manageable to read. Briefly explain what the WDT does. The watchdog timer WDT is a safety feature that helps prevent the microcontroller from hanging or getting stuck in an infinite loop. Here's a simple explanation. Watchdog timer WDT overview. Purpose. The WDT ensures that the microcontroller is running correctly. If the microcontroller stops responding or gets stuck, the WDT will reset it. Operation. The WDT runs independently of the main program and counts down from a set value. If it reaches 0, it triggers a reset. Clear the WDT. The main program must regularly clear the WDT using the clear WDT instruction to prevent it from reaching 0. This indicates that the program is running properly. Timeout period. The timeout period of the WDT can be adjusted using a prescaler, which changes how quickly it counts down. Simple example. Imagine the WDT as a timer that the microcontroller must reset periodically. If the microcontroller fails to reset the timer because it's stuck in a loop or not responding, the WDT will reset the microcontroller, forcing it to start over and potentially recover from the error. By using the WDT, you can improve the reliability of your microcontroller application by ensuring it can recover from unexpected problems. Okay, believe it or not, we're only halfway through the search of all of the instances of timer 0, and this is already the second video on the subject. Probably unnecessary for the listener to know that. But anyway, I already read this. Okay, timer 0 module and timer 0 register. I will read. Timer 0 module and timer 0 register. The timer 0 module has the following features: 8-bit timer/counter register. Timer 0, readable and writable, 8-bit software programmable prescaler, internal or external clock select, edge select for external clock from either TOCKI pin or from the output of the comparator. Figure 7.1 is a simplified block diagram of the timer 0 module. Show it quick here. Okay, maybe I'll read it first. TOCKI pin, internal comparator output, CMPOTCS. So a note to look that up. Then there's the TOSE, and this is an XOR logic gate. Once again, the TOSE is whether it should increment on a high to low or low to high. And the TOCS was the Timer0 clock source select bit, the TOCKI or the internal clock. Programmable prescaler selected using those 3 bits in the option register. Prescaler assignment. So what were the choices? WDT or Timer0. So the prescaler assignment, I guess, deals with that. Sync with internal clocks. Okay, so that would be one choice. Well, that was to do with the, well, whatever. I don't know. PS out sync Timer0 reg stuff. Okay, so I read the block diagram. Simple block diagram of the Timer0 module. Simple, yet I still don't understand it fully. Timer mode is selected by clearing the TOCS bit, option 5. In timer mode, the Timer0 module will increment every instruction cycle without prescaler. If Timer0 register is written, the increment is inhibited for the following 2 cycles. Figure 7.2 and 7.3. Oh boy, I never understand these ones. 7.2, 7.3. The little timer things are more stretched out on this one with the prescale of 1 to 2. This is no prescale. Oh, I'm still recording. Okay, yeah. Okay, the user can work around this by writing an adjusted value to the TMR0 register. There are 2 types of counter mode. The first counter mode uses the TOCKI pin to increment Timer0. It is selected by setting the TOCS bit. Setting the CMPTOCS bit. Got to come back to that. CMCON 0, 4, and setting the COUTEN bit, the CMCON 0 bit. In this mode, Timer0 will increment either on every rising or falling edge of pins TOCKI. The TOSE bit, option 4, determines the source edge. Clearing the TOS bit selects the rising edge. Restrictions on the external clock input are discussed in detail in section 7.1 using Timer0 with an external clock. So note to self, and even a note below. Hopefully I could leave a note below to further study this. I might forget to cover this. I probably will. But if you want to use the TOCKI pin, you have to fart around and set it like 6 other bits. The second counter mode, so there are 2 types of counter mode. The first counter mode involves all these alphabet soup of bits, and the second counter mode uses the output of the comparator to increment Timer0. It can be entered in 2 different ways. The first way is selected by setting the TOCS bit, option 5, and clearing the CMPTOCS bit. This bit does not affect the mode of operation. This enables an internal connection between the comparator and the Timer0. The second way is selected by setting the TOCS bit, option 5, setting the CMPTOCS bit, the CMCON, and clearing the bit CMCON0. This allows the output of the comparator onto the TOCKI pin while keeping the TOCKI input active. Therefore, any comparator change on the Cout pin is fed back into the TOCKI input. The TOSE bit determines the source edge. Clearing the TOSE bit selects the rising edge. Restrictions on the external clock input as discussed in section 7.1 using Timer0 with an external clock with this, but we're not even using those chips anyway. The prescaler may be used by either the Timer0 module or the watchdog timer, but not both. The prescaler assignment is controlled in software by the control bit PSA option 3. Clearing the PSA bit will assign the prescaler to Timer0. The prescaler is not readable or writable. When the prescaler is assigned to the Timer0 module, prescale values of 1 to 2, 1 to 4, 1 to 256 are selectable. Section 7.2 prescaler details the operation of the prescaler. A summary of registers associated with the Timer0 module is found in table 7.1. So I read that. Okay, 7.2 Timer0 timing, internal clock, no prescale, timer timing, internal clock, prescale 1 to 2. Stop and pause and read registers associated with Timer0, Timer0, CMCON0. Put a note down below. Got to make a video on the CMCON0 option and the trace GPIO. But this pertains to the other types of chips, which is not the 10F200. So that's easy. I won't read it, so it won't be confusing. I might have accidentally read some of this stuff already, inadvertently. So let's scroll down all the instances of Timer0, even while I'm recording. I'm going to skip past this stuff. So I'm thinking that this 7.1 applies to these chips. This is a main heading and this is like a subheading. So we can go from here, skip past this, and then the next topic is the prescaler. Okay, I'm going to go back up to this chart and just point something out. Not that I really understand this, but here's the block diagram of the PIC10F200. Here's a timer, well, in this diagram. But notice that in the diagram of the other chips that are not the 10F200, this is another chip, there's a comparator next to the timer. So, I don't know, stuff I read already, it pertains to this chip. Okay, I think I'll leave things here for this video, and maybe the next video will be about the prescaler as related to Timer0. So I'm on page 29, still in the Timer0 search.